Hi, welcome to a lecture on radiation from a current moment, and that's for a current moment with arbitrary orientation and arbitrary position. To begin, as a preface, let me remind you that we have, in a previous lecture, worked out the radiation, that is, the electric field radiated by current moment, which is located at the origin of the coordinate system, and which is oriented in the z-hat direction. And that current moment is described in terms of a volumetric current density in the z-hat direction with current moment I naught delta L, amps times meters, times the spatial sampling function. And again, in a previous lecture, we have worked out that the radiated electric field, the electric field intensity, is, as long as the field point, the point of evaluation, is much, much greater than a wavelength away from the current source, is equal to this expression, where the electric field is oriented in the theta hat direction. We have this constant here. The magnitude and phase of the source appears here. Sine theta is what we refer to as the pattern. And then we have the spherical wave dependence here. So that's all old news. The question we'd like to address in this lecture is, what happens if we change the orientation of that current moment? Or what happens if we change the position of that current moment? We'd really like to know the solutions to those things, because then we can employ superposition. For example, we can arrange current moments along a line and adjust the current moment magnitude and phase along that line to model a dipole, a physical dipole, such as a half-wave dipole. We can also model things like patches. A broad class of patches can be modeled as current moments lined up along two opposite edges of the square patch. We can also use current moments to represent arrays. So a very broad class of problems can be treated as superpositions of current moments with arbitrary orientation and position. So first, let's consider arbitrary orientation. We'll keep the current moment at the origin, and we'll change its orientation. So the picture shown here on the left indicates the scenario. Here the current moment has been tilted away from the z-axis by this amount theta naught. And so we can imagine that there is a rotation in the z-axis to this new direction, z hat prime. So now we can imagine that the current moment has the exact same form, except the direction is z hat prime, where z hat prime is just this tilt of theta naught from the z-axis. And it barely requires any analysis to figure out what the new radiated field is going to be. We simply recognize that we will have some new unit vector, theta hat prime, which is to z hat prime what theta hat is to z hat. This constant is the same. This phase and magnitude of the current moment is the same. Instead of theta, we'll have theta prime, and then the spherical wave dependence again. So this is a rotation of coordinates problem. Shows up in many, many different problems in engineering. And we really merely need to find the expressions for theta hat prime and theta prime in terms of the original coordinate system. Once we do that, we can have an expression that works for any orientation. So the key idea is to find z hat prime, in other words, the direction of this axis here. And that's quite simple to do. It's given in terms of the original coordinate system, x hat, y hat, z hat, using this expression. The component of x hat is sine theta naught, cosine theta naught. The component of y hat is sine theta naught, sine phi naught. And the component of z hat is cosine theta naught. Now, there's many different ways you can derive this expression, but I'll simply point out that it's something you can get just by kind of looking at the picture. And you can check, for example, we can check to make sure this is actually a unit vector. It is. If you compute the magnitude of this thing, it is 1. And you can check that gives you the right result for special cases. Like when theta naught is 0, we get back z hat, as expected. And when theta naught is pi, we get minus z hat, again as expected. And when theta naught is pi over 2, that's tilting this thing into the xy plane, and phi naught equals 0, then we get x hat, and that all checks. There's a more formal way to do this, and this is described in a number of textbooks, including basic electromagnetics textbooks. But this is really all we need to get started. Okay, so now we want theta prime. So the way we look at this is that here's the original z-axis. Here is the new z-axis, z hat prime. And then here is the vector which points towards the field point, which we're calling r. So r is the field point, and r hat is the unit vector which points towards the field point. And then theta prime is the angle between those two things. So from very simple considerations, the definition of the dot product, we see that the cosine of theta prime is given by the dot product of z hat prime dot r hat. And so we simply take the arc cosine to get theta prime. There we go. Theta prime is just arc cosine of the dot product between these two vectors. Now we need theta hat prime, the unit vector which will correspond to the direction of the electric field radiated by this current moment. That's a little bit more complicated, but really doesn't require a whole lot of derivation. First, just look to see what theta hat prime is. It is the unit vector which points away from the z hat prime vector, just as theta hat points away from the z hat vector. So theta hat prime is given by this unit vector, which is pointing down and to the right, as shown in this picture. And also note that it's perpendicular to r hat, that is the unit vector which points towards the field point. So here's what we do. We note first that z hat prime cross r, taking the cross product, is this unit vector right here that points into the page. This is the right-hand rule. You take the curled fingers of your right hand, start at z hat prime, let the fingers curl towards r hat, and your thumb points into the page. So this is the cross product of those two vectors. And then because the vector we seek is perpendicular to r hat, we can simply then take the cross product one more time to get theta hat prime. So the scheme is first we find this vector, we convert it into a unit vector by dividing by its magnitude, and then we take that result and take the cross product with r hat to get theta hat prime. That's the trick. So this is a general expression which will give us theta hat prime being the orientation of the electric field for this current moment, which is pointing in the z hat prime direction. So this completes a solution for an arbitrary orientation of the current moment as long as it's located at the origin. But now we want to consider translation from the origin to some position, and we'll call that position capital P. So now the current moment exists here, and it's oriented in the z hat prime direction. The only thing that changes in our mathematical definition of that current moment is the spatial sampling function, where now we want that spatial sampling function to trigger not at the origin, but rather at point P. So we indicate that simply by saying that the argument should be r minus P. Then we see that the associated electric field should be theta hat prime, which could change a little bit from before. We'll see that in a moment. And theta prime. So we have those two things. And we also note that the spherical wave dependence now has its origin at point P, so it's going to be convenient to find r prime. R prime is this distance shown here from the source point to the field point. Or mathematically, we can call r prime the magnitude of the difference vector r minus p. So the expression looks very, very similar, but what's changed is these two things a little bit, and then r prime instead of just r. So now if we work out what theta prime and r hat prime are going to be, well, we've already done the work. Theta prime is just arc cosine z hat prime dot r hat prime. This is different because r hat has become r hat prime. And theta hat prime is just going to be given by the same expression we had before, again with r hat replaced by r hat prime. So the solution for the displaced current moment really looks very similar to the solution for the current moment at the origin if we make this replacement based on this definition of r prime being with respect to the displaced source position. And that's really all there is to it. This completes the solution for arbitrary orientation and a displaced source position. Now, another thing to consider here is that we are almost always, not always, but almost always interested in the special case where the distance to the field point is much, much greater than the displacement between the source and the origin. And by that I mean, this is what we have in general. We have the origin, we have the source point, and we have the field point. But oftentimes, this represents an antenna, and this distance here is within the antenna, and this distance here goes to a distant field point. And in this case, where the distance to the field point is much, much greater than any dimension measured within the antenna, then the scenario looks very much like what I've got here, where these two rays, that is the ray that points to the field point starting at the origin, and the ray that points to the field point starting at the source, are approximately parallel. As you extend the field point very far away, these two rays are going to be approximately parallel. And in that case, we have a simple geometry problem where the distance is really just this distance here minus this distance, which is a projected distance. Specifically, it's a dot product of the position vector to the source with r hat. So in other words, we see that r prime, which is exactly the magnitude r minus p, is approximately equal to this distance, r, minus the projected distance, p dot r hat. And that's quite useful. Reason is because the spherical phase dependence goes as e to the minus j beta r prime. And so we know when we have this condition where the field point is far away relative to any spacing on the antenna, we can make the substitution. And then we can factor that into two factors. The first being e to the plus j beta p dot r hat, and the second one being e to the minus j beta r. And e minus j beta r is a spherical wave emanating from the origin as before, and then this factor is a correction. It's a modification to account for the fact that the source is not at the origin. So it's a modification to the phase pattern, as we say. And only this factor depends on theta and phi. This factor does not. This dramatically simplifies problems where we are studying superpositions of current moments. Furthermore, we don't have just e to the minus j beta r prime, we have e to the minus j beta r prime divided by r prime. That's a spherical wave. The denominator there represents the magnitude dependence. So we've already determined that in this condition where the field point's far away, we have this, at least approximately. But we can replace in the denominator r prime simply with r, that is the distance from the origin. And the reason we can do it in the denominator is because the denominator affects only the magnitude. It has nothing to do with the phase. And the incremental amount represented by the projected distance that we're accounting for in the phase dependence is negligible in terms of computing the magnitude. Said differently, if we move the current source by a fraction of a wavelength, we have to account for the phase. But moving the source point by a fraction of a wavelength has hardly any effect on the magnitude. And that's what we're indicating in this approximation. So, let's summarize what we've got. An arbitrarily oriented current moment at position P is given by this very slightly modified expression for the volumetric current density. And under this assumption that the distance between the field point and the source point is much, much greater than the wavelength, and that the distance to the field point is much, much greater than the displacement of the source point from the origin, then we get this expression for the electric field intensity, which looks very much like the original expression that we started this lecture with the distinction that we have this rotation of coordinates. In other words, primed coordinates instead of unprimed coordinates. We still have the same spherical wave dependence, but we have this factor which accounts for the phase which is induced by the change in position. And that's really all there is to it. I'll conclude this lecture by saying this form of the solution makes it relatively easy to construct solutions for complicated current distributions using superposition, as I alluded to at the beginning of the lecture. In other words, now that we have this expression, it becomes quite simple to construct any of these types of problems. This concludes the lecture.